Okay, in this video, we're going to cover how you name ionic compounds. And so we're going to follow a systematic way to name ionic compounds, and we'll see it's the same way that we'll end up naming covalent compounds. Or there is a system for each, is what I mean to say. And so when you're naming an ionic compound, first you want to make sure that you actually do have an ionic bond present. And so that means you're going to make sure that whatever compound you're looking at, it has a metal and a nonmetal in most cases. So right now we're worried about the so-called binary. So just two different types of elements. So binary ionic compounds. And so once you verify that you have a metal plus a nonmetal, the way we're going to name things is going to depend on if your cation always takes on one charge, so if it is only ever one charge, or if it can take on multiple. And what that really means is if you have one of the metals that are colored in this periodic table, so something from your alkali and alkali earth metals, basically, plus these three specific ones here, so silver, zinc, and aluminum, we're going to name using the first way. If instead the metal you have is one of those that can change charges, so the so-called transition metals, so everything in this block, columns 3 through 12, then you're going to specify what is the charge on that metal. And so we're going to look at, make sure we have a metal plus a nonmetal, and then we're going to name it one way if we have only one type of ion, name it a second way if we have two types of ions. Okay? And so first we're going to focus on the naming scheme used for what we'll say are the invariable cations. So those cations that are colored in or in a periodic table that are always going to have the same charge. And so, as I stated previously, we're focusing on what we call binary compounds, which are those that only have two different elements. And so the way that we're going to name these is we're going to write the name of the cation, so the name of the metal, and then we can write down the nonmetal and then check this table off to the right, which basically tells us what we're going to do to break something down into its base name. And then we're going to add IDE to that base name. And what we'll see is really, we're going to largely take the INE off a lot of these different compounds or the GEN and then substitute it out for IDE. And so if we look at this one that has calcium and oxygen, we can write our metal as calcium. We can write our nonmetal as oxygen. And let's just do that for each of the other ones. So we have KCl, so that's going to be potassium. And then your nonmetal is going to be chlorine. And then finally, ALN. Al is aluminum. And N is nitrogen. And then what we're going to do now is we're going to look at what the base name of each of our nonmetals are. So if we go over here, we can find oxygen. In the first case, we see that the base name is just OX. So we're going to cross off YGN, and we're just going to add IDE instead of that YGN. We can find chlorine, which is right here. So I'll put this number 1 for oxygen, number 2 for chlorine. We see that its base name is CHLOR. So we're going to get rid of INE and substitute IDE. Then we can find nitrogen. So that's number 3 here. We see that nitrogen's base name is NITR. So we get rid of OGEN. We add IDE. And so the way that we name each of these is we take the name of our metal, so calcium. Then we add the base name of the anion plus IDE. So what we have, OX in black and then IDE in red. So calcium oxide. For KCl, we'd say potassium because we have the name of our metal, plus nonmetal base name plus IDE, chloride. And then finally, we have aluminum, the name of our metal, plus base name of the anion, so base name of your nonmetal plus IDE, nitride. So what's in black plus what's in red, okay? And so the way that this is how we name these invariable cations. The way that we name our so-called variable cations, so the ionic compounds that have a transition metal as opposed to one of these other metals, is all that we really have to do is we have to just specify the charge because that's ambiguous until we state it. And so we just have to specify which one. And the way that we'll be specifying that is using Roman numerals. So when we have an iron 2 plus, the way that we'll name that is we'll say the name of the metal, iron, and then we'll just put whatever that charge is in brackets or in parentheses, and then we write down the charge using Roman numerals. So 2, slashes for iron for like the number 2. And then for iron 3, we just write iron, put in parentheses the charge 1, 2, 3, using about Roman numerals. And we just want to remind ourselves that an I is equal to 1, so I is 2, I is 3, and then IV is 4, V is 5, and then VI is 6. And of course, you don't have to write that top and bottom bracket that brings them all together, specifically when we have V's. I will end up writing them, but we just need to remind ourselves what that looks like. But once you include in parentheses the charge of that of each of your metals, you can see that the last little bit of it is just the same as before. You take the base name of the anion plus IDE. And so we're going to look at two different cases here. So we have cobalt, which is our metal. And so far, we actually can't tell what the charge is. So what we're going to do is we're going to use the charge on the other component to help us determine what the charge on our metal is. So we know our nonmetal is sulfur. And if we look up at what our nonmetal is, sulfur, we look up at our little table from a couple slides ago. So I believe it's this one right here. We can find sulfur right here, and we see that sulfur typically adopts a -2 charge. So we can come down here, we can say that sulfur is typically a -2, and we know that we have a single one of those because we have that COS. And so the net anionic charge, the net minus charge is -2. And so to balance out the charge, if we only have one cobalt, that means it must also have a 2 charge. So it must be cobalt 2. And so then the way that we name this is we have cobalt 2, the name of our metal. We have its charge in parentheses as that Roman numeral. And then we look at sulfur. Its base name is going to be SULF. We cross off the UR. We change that out for IDE. And the way that we'd name this is we'd call this cobalt 2 sulfide. So this is cobalt 2 sulfide. We go down to the next one. This is also cobalt. And we're going to do the same thing as before. We're going to use the charge on our anion to figure out what the charge on our cation is. So we know that our nonmetal here, Cl, is chlorine. We know that the charge on chlorine is -1 because it's in that halogen row. And here we notice we have 3 of them. So we have 3 times -1. That means the net anionic charge from your nonmetal is -3. So to get charge neutrality, if we only have one metal, one cobalt, it has to come up with all the positive charge. So we'd say that our cobalt is cobalt 3 plus. So this is CO3 plus to balance out the 3 minuses from 3 chlorine minuses. This is cobalt 2 plus to balance out the charge from a single sulfur 2 minus. And so the way that we name this, we have chlorine becomes chloride, so IDE. So we have cobalt 3 chloride. Okay. And so, like I just mentioned earlier, so we can use the total charge of your anionic portion to figure out the charge of the cationic portion. And so what I'll have you do right now is I'll ask you to pause the video and then using the charge of your anion, which in this case is oxygen, I want you to try naming each of these different compounds. So pause the video here. Okay, welcome back. So if we looked up oxygen in our table above, we'd see that oxygen typically has a 2 minus charge. So if you have a 2 minus charge from oxygen here, you only have one copper. Effectively, what you have is X minus 2 has to equal a charge of 0. The only value you can have here is X must be 2 as well. So X must be equal to plus 2. So that would give us that this is copper 2 plus. And we can do the same thing over here. We have O2 minus, and in this case, we have 2 coppers. And so this is the same as saying 2 times the charge of copper plus negative 2 equals 0. And if we look at this, we could say, like 2 equals 2, divide by 2, divide by 2. In this case, x equals 1. So here we'd say that each of our coppers only comes with a plus 1 charge because we have 2 of them to compensate for the 2 minus charge from oxygen. We could have done the same, algebra here, x minus 2 equals 0, so x equals 2. So the way that we name these is we call the first one, because it's a copper 2 plus, we'd say copper, put its charge in parentheses, 2, oxide. And for a second one, we have copper. That's the name of our metal. In this case, our charge is only a 1, and then we'd also put oxide here. And so you could see these names are both copper oxide, but the thing that changed was the 1 or the 2 that kind of describes the charge. Okay? And this algebraic form of, breaking it down to, charge on your metal, which we called X, plus charge on your nonmetal, which in this case was minus 2, equals neutrality, is a really easy way to figure out the charges on your transition metals. And so one other type of ionic compound that you can form is one using something called a polyatomic ion. And so what this polyatomic ion is it's a group of covalently bonded or covalently bound atoms, which we'll talk about covalent bonding with in a second, with an overall charge. And these covalently bound ions are known as polyatomic ions. Poly, because you have multiple ions, poly for multiple atoms. And then ion for the fact that it's charged. And then ion for charge. And so things like bleach, baking soda, and Tums have one of these polyatomic ions. And when we think about these polyatomic ions, one thing we always want to think about, or one thing to know, is that the charge of the polyatomic ion is a property of the whole ion. Or another way to say it, property of whole ion. Another way to say this is that charge is shared by all the atoms. So charge shared by all atoms. And so I'm just going to provide you a quick couple examples of these polyatomic ions. So I said that bleach has one of these, and the name for the ionic compound in bleach is sodium hypochlorite. And so in this case, the formula for that is NaClO. And so we know that Na is just simply the metal sodium. So that means that our polyatomic, that thing which is called hypochlorite, must be ClO. And to get charge neutrality, if sodium comes in with a plus, this hypochlorite must come in with a minus. Another example of this is the sodium bicarbonate, which is by definition what baking soda is, sodium bicarbonate. And the formula for this is simply sodium and then HCO3, where your polyatomic here is, everything but the sodium. So that HCO3, and then if sodium has a plus charge, that must mean HCO3 has a minus charge to have charge neutrality. And then the final one is the active ingredient in Tums, which is calcium carbonate, which is also what makes up seashells, where the compound here, as well as in part bones, is calcium CO3. We know that calcium is a 2 plus, and we know that's the metal portion. So our polyatomic must be everything else except for the calcium. So that's CO3. And if calcium has a 2 plus, that CO3 must have a 2 minus. And what you might notice is that these last two examples, the bicarbonate and the CO3 carbonate, are essentially the same with just a change of a hydrogen. And so if we look up a table of these polyatomics, we'll see that some of them are actually part of a family. So we have things like phosphate, hydrogen phosphate, and dihydrogen phosphate, where you're just adding hydrogens, and each time you add a hydrogen, it changes the name of your polyatomic. And by and large, these polyatomic ions are going to be anions. You can see that most of the species here have a minus charge. Acetate does, carbonate does, hydroxide does. The one exception is this bottom one on the left column, ammonium. Ammonium is basically, for all we're worried about, is our one example of a non-metal cation, or in this case, a non-metal polyatomic that makes a cation. And so NH4 plus is this non-metal cation, and it can form a bond with a non-metal anion like chlorine. This is a non-metal anion. And so this is one thing that kind of breaks our rule that an ionic bond is formed between a metal and a non-metal. Because here we have two nonmetals, or rather, well, really three nonmetals, but a non-metal cation forming a bond with a non-metal anion. But we still describe this as an ionic bond because it's between a anionic chlorine and a cationic ammonium. So it's between a polyatomic ion that this charge is shared by that whole NH4, and it's being formed between an anion with chlorine. And so the important thing here is that there's still a net transfer of electrons, or more specifically, we have two charged species interacting with each other. Okay. And so if there's ever a case where we're looking at these multiple polyatomics and we end up needing more than one of a polyatomic, we have to think about how we want to notate that. Because up to this point, we've been worried about these binary compounds where all you had to do was add a subscript. But here, because these polyatomics are multiple ions, we have to know how to add that subscript. So let's look at something like magnesium hydroxide. So you have magnesium and you have hydroxide, which we can find in this table right here. So we know that magnesium, if we look up its typical charge, typically has a 2 plus charge, and hydroxide typically has a 1 minus charge here. And we can equate this to if we had something like magnesium chloride. So magnesium 2 plus, chlorine minus. We know that when we did this, all we did was we took the 2 plus on magnesium, we stuck it over here. You took the 1 from chlorine minus, you stuck it over here. And so you got Mg1Cl2, which is the same as MgCl2. And so in the same vein, where we had a single magnesium with two chlorines, we also want to have a single magnesium plus two hydroxides. And the way that we'll notate this when we form our compound is we'll take our polyatomic in parentheses and put that subscript of 2, which this 2 right here, to say how many of it we need. So we'll say Mg, we have a single one of those. Then we write down the identity of our polyatomic, and then since we want 2 of those, we'll put the 2 right here. So it's the same thing that we did with magnesium chloride, but instead of just straight up putting the subscript, we had to put the whole hydroxide in parentheses so that we're saying we have 2 of this polyatomic hydroxide, 2 of this unit that gives a single negative charge. Because if we wrote something like this, MgOH2, that would mean something different. Because that charge is shared by all of hydroxide, and here you're just saying, oh, I'm adding another hydrogen, which is not what's actually happening with the formation of the magnesium hydroxide. We want to make sure that we're saying that we have 2 oxygens and 2 hydrogens that come with it. Okay. And so what I'll have you do right now is I'll have you pause the video, and then I want you to try to name these. And so you want to remember that when you name these ionic compounds, you're looking at if you have variable or invariable metal cation, because that determines if you choose to use or not use the Roman numeral notation. So pause here, and then we'll name all of these. Okay. All right, welcome back. So if we look at each of these, we can see that some of these have variable cations, some of these have invariable cations, and some of them actually have polyatomic cations. We also have some polyatomic anions. And so if we look at our first one, PbCl4, we know we can, when we find Pb, which is lead, we see that it sits in those transition metals. So we know that we have lead, and we have Cl, which is CHLOR for its base name plus IDE. And if we look at that, we know we have 4 chlorines, and each of them adopts a -1 charge. So those are chlorines. So that means that the net negative charge from chlorine must be -4, and so that means that our lead must be +4. So we'd say this is lead 4 chloride. Okay. Our next one we have is sodium is our metal, and then we see that our nonmetal, which in this case, or our anion, is a polyatomic. We look up the name of that polyatomic, and that's hydroxide. So we don't have to do any dropping of base name to named name because all the polyatomics already take into account this naming scheme. Our next one, our metal is lithium. So we can just write down lithium. We see that our nonmetal is F, which is fluorine. And so we can write down the base name of fluorine, which is FLUOR. And then we add IDE to make lithium fluoride. Our next one is tin. And if we look up tin, we can see that this is one of those metals that change their charge. So we're going to put its charge in parentheses, and our anion is cyanide. So we can write down the name of that species, cyanide. And if we look up the charge of cyanide, it's this. So it's cyanide minus. And so since we have 2 cyanides, that we have 2 times -1. So that's -2. So then your tin, to get charge neutrality, must be +2. So we'd say this is tin 2 cyanide. And then finally, we have this last species here, which is NH4I. This was our one exception of our nonmetal cation, which is called ammonium, if we look that up in our table above. And then the anion is the nonmetal iodine. So we can write down its base name, IOD plus IDE for iodide. So that's the names of each of these. Okay. So the last thing we'll do with naming these ionic compounds is going to be those that contain, or is going from a name to the actual formula. And so here, what you're going to want to do is you're going to want to figure out the charge of each of the species, charge of each species. And then with that in mind, you're going to figure out number of each. So you're going to utilize that cross multiply. And so I'll let you pause the video right here, and then we'll come back and talk through each of these. Okay. All right. So pause. All right. So welcome back. So we can, break this down just like we said we were going to. So we can look at zinc, and zinc was one of those transition metals that still typically adopts a specific charge. In this case, it's 2+. We look up nitrate, which is this following structure right here, and we look and see that it has a -1 charge. So we do that cross multiply. 1 goes here, 2 goes here. So we have zinc 1, which I'll just omit the 1. And then we have nitrate. We have 2 of those. And since we're doubling the number of the polyatomics, we make sure to put it in parentheses. So make sure to use parentheses. Sure to use parentheses. Okay. Next, we do aluminum sulfide. Aluminum also typically adopts a single charge. That's 3+. Sulfide is sulfur with a 2-. We do the switcheroo, and we get Al2S3. And so can't reduce that down any further, so that's our answer there. Next, we have calcium oxide, so Ca2+, O2-. We do the cross multiply. We get that that's Ca2O2, and we see that we can actually reduce this down by dividing both the subscripts by 2, so we get CaO. And of course, in this case, if you see that you have charge neutrality, you don't have to do the cross multiply and reduce. you can just write down calcium oxide. This next one, we have chromium 2 sulfate. So we see now we have a variable cation. So write Cr2 plus. We write down sulfate. We can look up in our polyatomic table. We see that's SO4 2 minus. This is another one where we can cross multiply. And we see that we're multiplying everything by 2. So we get Cr2. That's not what I wanted. So we have Cr2, SO4, 2. And then we can divide by 2. So we divide all the subscripts by 2, and we get CrSO4. And that's the same thing we did here. So we divide by 2. And then our last one is mercury bromide. So mercury is one of the weird ones that its Latin name is different than its English name. So that's Hg, and then we have a 2 plus here. We have bromine is a single 1 minus. Do the cross multiply, and we get that that's Hg1, I'll omit the 1, Br2. Okay? All right, and so that's where I'll end this lesson. And next we're going to talk about naming ionic compounds that have water within them as well as acids.